Have you ever wondered what it would be like to witness the birth of a star? To see matter itself transform from the cold emptiness of space into a blazing furnace that will burn for billions of years? Well, what if I told you that right now, scattered across our galaxy, there are cosmic nurseries where baby stars are taking their very first breaths, and the process is more violent, more beautiful, and more essential to our existence than you could possibly imagine. Tonight, we're going to journey into the heart of stellar birth, where temperatures reach millions of degrees, where gravity wages war against the fundamental forces of nature, and where the raw materials that make up your body were forged in nuclear furnaces beyond comprehension. And I promise you, by the end of this exploration, you'll never look at the night sky the same way again. If you find yourself captivated by these cosmic mysteries, I'd be incredibly grateful if you'd consider hitting that subscribe button and ringing the notification bell. The universe has so many secrets to share, and I want to take you on every single journey. Now, before we dive into the incredible physics of how stars are born, let me share something that will completely change your perspective on your place in this vast cosmos. Every single atom in your body, except for hydrogen, was created inside the core of a dying star. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged in stellar furnaces and scattered across space in violent stellar explosions billions of years ago. You are literally made of stardust, and the story of how stars are born is ultimately the story of how you came to exist. But here's what makes this even more extraordinary. Right now, at this very moment, new stars are being born in our galaxy at a rate of about 1 every year. That means while you're watching this video, somewhere in the Milky Way, a massive cloud of gas and dust is collapsing under its own gravity, heating up to unimaginable temperatures, and igniting nuclear fusion for the very first time. It's like cosmic fireworks happening continuously across the universe. The process of star formation is one of nature's most spectacular performances, and it begins in the most unlikely places, in the cold, dark regions of space called molecular clouds. These aren't the fluffy white clouds you see in Earth's sky. These are massive, ethereal structures that can span hundreds of light years across and contain enough material to create thousands of stars like our Sun. Picture this. Imagine a region of space so vast that light takes centuries to travel from one side to the other, yet so cold that temperatures hover just a few degrees above absolute zero. The density is so low that it makes the best vacuum we can create on Earth seem thick as soup. Yet within this seemingly empty void, something magical is about to happen. These molecular clouds are primarily composed of hydrogen and helium, the most abundant elements in the universe, along with tiny traces of heavier elements created by previous generations of stars. But here's the fascinating part. These clouds aren't uniform. They're filled with subtle variations in density, temperature, and composition that will ultimately determine where and how new stars will form. Think of it like a cosmic symphony, where every instrument needs to play at exactly the right moment. The slightest disturbance, perhaps a shockwave from a nearby supernova, the gravitational influence of a passing star, or even the rotation of the galaxy itself, can trigger a cascade of events that leads to stellar birth. It's as if the universe is constantly setting up the perfect conditions for creation. When one of these disturbances occurs, something remarkable begins to happen. The delicate balance that has kept the molecular cloud stable for millions of years suddenly shifts. Gravity, that weakest of the fundamental forces, yet the most persistent, begins to win a cosmic tug-of-war against the thermal pressure that has been keeping the cloud expanded. As gravity takes hold, the cloud starts to contract. But this isn't a gentle, gradual process. It's more like a slow-motion avalanche where different regions of the cloud begin collapsing at different rates. Some areas become denser more quickly, creating what astronomers call dense cores, the seeds from which individual stars will eventually emerge. Here's where the physics gets absolutely mind-blowing. As these dense cores contract under their own gravity, something counterintuitive happens. They actually get hotter. This might seem backwards at first. After all, when you expand a gas, it typically cools down, so you might expect a contracting gas to cool as well. But in space, the rules are different. The gravitational potential energy of the collapsing material gets converted into kinetic energy, the random motion of particles that we experience as heat. It's the same principle that makes a bicycle pump warm up when you use it, but scaled up to cosmic proportions. As the dense core continues to collapse, temperatures begin to rise from a frigid few degrees above absolute zero to hundreds, then thousands of degrees. But here's the truly spectacular part. This process takes an incredibly long time by human standards. While the initial collapse might begin relatively quickly in cosmic terms, the journey from a cold molecular cloud to a fully formed star takes millions of years. It's a process that spans dozens of human generations, yet from the perspective of the universe, it's barely a blink of an eye. As the collapsing core continues to heat up and compress, it begins to glow. At first, this glow is invisible to human eyes. It's in the infrared part of the electromagnetic spectrum, detectable only by specialized telescopes. But this infrared radiation tells an incredible story. It's the signature of a protostar being born. A protostar is essentially a star in training. It has many of the characteristics we associate with stars. It's hot, it glows, it has its own gravitational field, but it lacks the one crucial feature that defines a true star: nuclear fusion. The core isn't yet hot or dense enough to force hydrogen nuclei to overcome their mutual repulsion and fuse together to form helium. During this protostar phase, which can last for hundreds of thousands of years, something absolutely beautiful happens. The growing star begins to interact with the surrounding material in the molecular cloud, creating some of the most stunning visual displays in the cosmos. Jets of hot gas shoot out from the protostar's poles at incredible speeds, sometimes traveling at hundreds of kilometers per second. These jets carve through the surrounding material like cosmic lightsabers, creating intricate structures called Herbig-Haro objects. When you see images of these phenomena, they look almost like abstract art painted on the canvas of space. Flowing ribbons of glowing gas in brilliant reds, blues, and greens, sculpted by invisible magnetic fields and powered by the tremendous energy of stellar birth. But the protostar isn't just creating beautiful light shows, it's also fundamentally altering its environment. The intense radiation and powerful stellar winds blow away much of the surrounding material, gradually clearing out a cavity in the molecular cloud. This process is crucial because it prevents the growing star from accumulating too much mass too quickly, which could lead to instability or even collapse. Meanwhile, some of the material that isn't blown away begins to form a rotating disk around the protostar. This disk is incredibly important because it's where planets will eventually form. The same gravitational forces that created the star also organize the leftover material, into a flattened, spinning structure that will serve as the nursery for an entire planetary system. As we watch this cosmic dance unfold, we're witnessing the same processes that led to the formation of our own solar system 4.6 billion years ago. Our Sun was once a protostar, surrounded by a disk of material that eventually coalesced into the planets, moons, asteroids, and comets that populate our cosmic neighborhood today. The transition from protostar to true star happens gradually, but there comes a moment, a critical threshold, when everything changes. As the core continues to contract and heat up, the temperature and pressure eventually reach the point where nuclear fusion can begin. This typically occurs when the core temperature reaches about 10 million degrees Celsius. At this magical moment, hydrogen nuclei begin to fuse together to form helium, releasing tremendous amounts of energy in the process. This is the moment when a star truly ignites, when it begins to shine with its own light powered by the same nuclear reactions that fuel hydrogen bombs, but sustained and controlled by the star's own gravity. The energy released by nuclear fusion creates an outward pressure that exactly balances the inward pull of gravity. This delicate equilibrium, called hydrostatic equilibrium, is what allows stars to maintain their size and brightness for billions of years. It's like a cosmic balancing act, where two fundamental forces reach a perfect standoff. But not every protostar makes it to this stage. The universe is littered with failed stars called brown dwarfs, objects that formed like stars, but never quite accumulated enough mass to ignite nuclear fusion. These cosmic misfits exist in a twilight zone between stars and planets, slowly cooling over billions of years as they radiate away the heat from their formation. The mass of the original molecular cloud core determines what kind of star will eventually form. Small cores create red dwarf stars that burn slowly and steadily for trillions of years. Medium-sized cores, like the one that formed our Sun, create yellow stars with lifespans measured in billions of years. The largest cores create massive blue giants that burn bright and fast, live in spectacular but brief lives measured in millions of years. Each type of star plays a crucial role in the cosmic ecosystem. Red dwarfs are the universe's marathon runners, providing stable conditions for billions of years that could potentially support the long-term evolution of life. Sun-like stars create the perfect conditions for liquid water and complex chemistry in their habitable zones. Massive stars are the universe's element factories, creating and dispersing the heavy elements necessary for rocky planets and biological life. This brings us to one of the most profound realizations about stellar birth. It's not just about creating new lights in the sky. Star formation is the engine that drives cosmic evolution. Each generation of stars creates heavier elements through nuclear fusion and scatters them through space when they die. These elements become the raw materials for the next generation of stars and planets, gradually enriching the universe with the chemical complexity necessary for life. The story of star formation is ultimately a story of cosmic recycling on the grandest possible scale. The material that forms new stars has been through this cycle many times before. Some of the atoms in your body were forged in the first generation of stars that formed after the Big Bang. Others were created more recently in stellar furnaces that burned out just a few billion years ago. And someday, billions of years in the future, those same atoms will be incorporated into new stars and new worlds in a cycle that has no end. What's truly mind-blowing is that we can actually witness this cosmic recycling happening right now. Modern telescopes have allowed us to peer into stellar nurseries with unprecedented detail, and what we've discovered has revolutionized our understanding of how stars are born. Take the Orion Nebula, one of the most famous star-forming regions in our galaxy. Located about 1,300 light-years from Earth, this cosmic maternity ward is visible to the naked eye as a fuzzy patch in the constellation Orion. But when we point powerful telescopes at this region, we see something absolutely extraordinary. Hundreds of baby stars in various stages of formation, all clustered together in a stellar daycare center. What makes Orion so special is that we can see the entire star formation process playing out simultaneously. There are massive molecular clouds just beginning to collapse, protostars surrounded by swirling disks of material, newly ignited stars blowing away their birth cocoons, and fully formed stars that have settled into stable nuclear burning. It's like having a time-lapse movie of stellar evolution, except instead of showing one star over millions of years, we're seeing hundreds of stars at different stages all at once. But here's where things get really interesting. Recent observations have revealed that star formation isn't the chaotic, random process we once thought it was. Instead, it's remarkably organized and efficient. These stars don't form in isolation. They form in clusters, groups, and associations that follow predictable patterns governed by the physics of gravity, turbulence, and magnetic fields. Think of it like a cosmic assembly line. Massive molecular clouds fragment into smaller clumps, which then fragment further into individual star-forming cores. But this fragmentation isn't random. It's guided by invisible magnetic field lines that thread through the cloud like a cosmic web. These magnetic fields act like guidelines, channeling material towards specific locations where conditions are just right for star formation. The magnetic fields also play another crucial role that scientists are only now beginning to understand. As material falls toward a forming star, it carries magnetic field lines with it. These field lines get twisted and tangled, creating magnetic tension that can actually slow down the collapse and regulate how quickly the star accumulates mass. It's nature's way of preventing stellar formation from happening too quickly and creating unstable stars. But perhaps the most surprising discovery about star formation has been the role of stellar feedback. The way that newly formed stars influence their environment and the formation of future generations of stars. When a massive star ignites, it doesn't just sit there quietly burning hydrogen. It unleashes tremendous amounts of energy in the form of intense ultraviolet radiation and powerful stellar winds. This energy has a dramatic impact on the surrounding molecular cloud. The ultraviolet radiation heats up nearby gas, causing it to expand and become less dense. The stellar winds create shock waves that can either compress nearby regions and trigger new star formation, or blow material away and prevent stars from forming. It's a delicate balance between creation and destruction that determines how many stars will ultimately form in any given region. Some of the most spectacular examples of stellar feedback can be seen in regions like the Cygnus X complex, a massive star-forming region located about 4,500 light-years away. This region contains some of the most massive stars known to exist, and their combined energy output is literally reshaping the entire structure of the surrounding molecular cloud. Huge cavities have been carved out by stellar winds, while dense shells of compressed gas at the edges of these cavities are actively forming new generations of stars. It's like watching cosmic urban planning in action. The first generation of massive stars acts like cosmic bulldozers, clearing out space and creating the conditions for the next wave of star formation. This process can continue for millions of years, with each generation of stars influencing the birth of the next, creating a complex ecosystem of stellar formation and evolution. But star formation isn't just about the physics of gravity and nuclear fusion. It's also intimately connected to the chemical evolution of the universe. When the first stars formed shortly after the Big Bang, they had only hydrogen and helium to work with, the only elements that existed at that time. These primordial stars were fundamentally different from the stars we see today, likely much more massive and short-lived. When these first-generation stars died in spectacular supernova explosions, they scattered newly created heavy elements throughout space. Carbon, oxygen, nitrogen, silicon, iron, all the elements essential for rocky planets and biological life, were forged in the nuclear furnaces of these ancient stellar giants and distributed through the cosmos in their death throes. This cosmic enrichment process set the stage for the second generation of stars, which formed from material that was already slightly enriched with heavy elements. These stars could form planets, and some of those planets could potentially harbor life. Each subsequent generation of stars has continued this process, gradually increasing the heavy element content of the universe and making increasingly complex chemistry possible. Today, when we observe star formation in our galaxy, we're seeing this cosmic enrichment process in action. The molecular clouds from which new stars form contain trace amounts of heavy elements created by billions of years of stellar evolution. These elements play crucial roles in the star formation process itself, acting as coolants that help gas clouds collapse more efficiently, and as the raw materials for dust grains that facilitate further cooling and condensation. The dust grains are particularly important because they serve as tiny factories for molecular chemistry. On their surfaces, hydrogen atoms can combine to form molecular hydrogen, the primary constituent of dense molecular clouds. Complex organic molecules can also form on these dust grain surfaces, including some of the basic building blocks of life like amino acids and organic alcohols. This means that the process of star formation is simultaneously creating the conditions for life and producing some of the molecular ingredients that life requires. The same cosmic nurseries that give birth to new stars are also cosmic chemistry labs, producing the complex molecules that will eventually be incorporated into planets and potentially into living organisms. Recent studies using advanced radio telescopes have detected an astonishing variety of organic molecules in star-forming regions. We're talking about molecules with dozens of atoms, including complex sugars, alcohols, and even some of the chemical precursors to DNA and proteins. The implications are staggering. The molecular foundations of life are being laid down in the same processes that create new stars and planetary systems. This discovery has profound implications for our understanding of how life might emerge throughout the universe. If complex organic chemistry is a natural byproduct of star formation, then the ingredients for life might be far more common than we previously thought. Every new star system that forms comes preloaded with a toolkit of organic molecules that could serve as the starting points for biological evolution. But the story gets even more remarkable when we consider the timescales involved. The star formation process we've been describing doesn't happen in isolation. It's part of a much larger cosmic cycle that operates on truly astronomical timescales. The molecular clouds that give birth to stars are themselves created by the deaths of previous generations of stars. which enriched the interstellar medium with heavy elements and stirred up the galaxy's gas and dust through their explosive endings. This creates a cosmic feedback loop that has been operating for billions of years. Stars form, live their lives, create heavy elements, die, and enrich the interstellar medium, which then forms new molecular clouds, which collapse to form new stars, and the cycle continues. It's a process that connects the birth and death of stars across cosmic time, linking the very first stars that formed after the Big Bang to the stars being born today, and to the stars that will form billions of years in the future. The efficiency of this cosmic recycling system is truly remarkable. Astronomers estimate that the material in our galaxy has been recycled through multiple generations of stars many times over. The carbon in your DNA has probably been through at least a dozen different stars over the course of cosmic history. The oxygen you breathe has traveled through space for billions of years, spending time in stellar cores, planetary nebulae, supernova remnants, and molecular clouds, before finally ending up in your lungs. This perspective fundamentally changes how we think about our place in the universe. We're not just observers of cosmic processes, we're active participants in them. We're temporary arrangements of stellar material that has achieved the remarkable ability to contemplate its own cosmic origins. When you look up at the night sky and see stars being born in distant nebulae, you're witnessing the same processes that created the very atoms that make up your body and brain. The technology that allows us to study star formation has advanced dramatically in recent years, giving us unprecedented insights into these cosmic nurseries. Space-based infrared telescopes like the James Webb Space Telescope can peer through the dust and gas that shrouds star-forming regions, revealing the hidden details of stellar birth. Radio telescopes can detect the molecular signatures of complex chemistry happening in these regions, and computer simulations can model the complex physics of gravitational collapse, magnetic fields, and stellar feedback with incredible precision. These tools are revealing that star formation is even more complex and fascinating than we ever imagined. We're discovering that the process varies dramatically depending on the environment. Stars form differently in the dense cores of galaxies compared to their sparse outer regions. The presence of nearby massive stars, the strength of galactic magnetic fields, and even the orbital dynamics of the galaxy itself all influence how and where new stars will form. We're also learning that star formation is intimately connected to the evolution of galaxies themselves. The rate at which a galaxy forms new stars determines its color, its chemical composition, and ultimately its fate. Galaxies that form stars rapidly tend to be blue and rich in heavy elements, while those with slower star formation rates appear redder and more chemically primitive. This connection between stellar birth and galactic evolution means that understanding star formation is crucial for understanding the universe as a whole. The cosmic history of star formation tells the story of how the universe evolved from a simple collection of hydrogen and helium gas into the complex, chemically rich cosmos we see today, filled with galaxies, stars, planets, and life. One of the most mind-bending aspects of stellar formation that astronomers have recently discovered is that the process isn't just happening randomly throughout space. It's orchestrated by cosmic forces operating on scales so vast, they make our solar system look like a grain of sand on a beach. The spiral arms of our galaxy act like massive compression waves, sweeping through the Milky Way's disk and triggering star formation wherever they encounter molecular clouds. Picture this cosmic choreography unfolding over millions of years. As our galaxy rotates, these spiral density waves move through space like slow-motion tsunamis, compressing gas and dust in their wake. When a molecular cloud encounters one of these waves, it's like a cosmic trigger being pulled. The additional gravitational pressure is often just enough to tip the balance and initiate the collapse that leads to stellar birth. This means that star formation in our galaxy follows a predictable pattern, with new stars being born preferentially in the spiral arms, where these compression waves are strongest. It's why the spiral arms of galaxies often appear brighter and bluer than the regions between them. They're illuminated by the intense radiation of young, massive stars that have recently ignited. But here's where it gets truly extraordinary. The stars that form in these spiral arms don't just sit there. They continue orbiting the galaxy at their own speeds, which are often different from the speed of the spiral pattern itself. This creates a cosmic conveyor belt effect, where stars are born in the spiral arms, but then gradually drift away from their birthplaces over millions of years. Our own sun is a perfect example of this process. Based on its current location and orbital characteristics, astronomers believe our sun was likely born in one of the Milky Way's spiral arms about 4.6 billion years ago, but has since wandered into the relatively quiet region between spiral arms where we find ourselves today. In a sense, we're living in the cosmic suburbs, far from the stellar nurseries where new stars are actively being born. The implications of this galactic-scale organization of star formation are profound. It means that different regions of the galaxy have experienced very different histories of stellar birth and chemical enrichment. The central regions, where the stellar density is highest and star formation has been most active, are rich in heavy elements created by generations of stellar evolution. The outer regions, where star formation has been more sporadic, remain more chemically primitive. This chemical gradient across the galaxy has direct implications for the potential for life to emerge in different regions. Planets forming in the metal-rich inner regions have access to more of the heavy elements necessary for rocky planet formation and complex chemistry. Those in the outer regions might struggle to accumulate enough heavy elements to form substantial rocky worlds. But there's a delicate balance at play here. While heavy elements are necessary for planet formation and life, too much stellar activity can also be dangerous. The central regions of galaxies are violent places, filled with massive stars that explode as supernovae, black holes that devour surrounding material, and intense radiation fields that could sterilize any nearby planets. The Goldilocks zone for galactic habitability, not too active, not too quiet, but just right, might be in regions like where our solar system currently resides. Recent observations have revealed another stunning aspect of star formation that challenges our understanding of how these processes work. Using powerful telescopes, astronomers have discovered that many stars don't form alone. They form in multiple systems, with 2, 3, or even more stars orbiting around their common center of mass. In fact, binary and multiple star systems might be the norm rather than the exception in our galaxy. This discovery has revolutionized our understanding of stellar birth. It turns out that the fragmentation process we discussed earlier often doesn't result in single, isolated stars. Instead, the collapsing cores of molecular clouds frequently break apart into multiple fragments, each of which can become a star. These stellar siblings are born together from the same cosmic material and begin their lives in complex orbital dances around each other. The dynamics of these multiple star systems are incredibly complex and beautiful. In some cases, two stars of similar mass orbit each other in nearly circular paths, locked in a cosmic waltz that can continue for billions of years. In other systems, one star might be much more massive than its companion, leading to dramatic interactions as the larger star's gravity strips material from the smaller one. These stellar interactions can create some of the most spectacular phenomena in the universe. When material flows from one star to another in a binary system, it doesn't fall directly onto the star's surface. Instead, it forms a swirling disk called an accretion disk, which can heat up to millions of degrees and emit intense X-rays and other high-energy radiation. Even more dramatic are the cases where binary stars eventually merge with each other. When two stars spiral inward due to the emission of gravitational waves, ripples in space-time itself, they can eventually collide in cataclysmic events that release more energy in seconds than our Sun will produce over its entire 10 billion year lifetime. These stellar mergers are thought to be responsible for some of the most powerful explosions in the universe, including certain types of gamma-ray bursts that can be detected across billions of light years. The study of stellar mergers has taken on new significance in recent years with the development of gravitational wave detectors like LIGO and Virgo. These incredibly sensitive instruments can detect the tiny distortions in space-time caused by merging stellar objects, giving us a completely new way to study these cosmic catastrophes. The gravitational waves from stellar mergers carry information about the masses, spins, and compositions of the merging objects that we could never obtain through traditional astronomy. But perhaps the most exciting aspect of studying multiple star systems is what they tell us about planetary formation. We now know that many of the exoplanets discovered orbiting other stars exist in binary or multiple star systems. This raises fascinating questions about how planets form and evolve in these complex gravitational environments. In some cases, planets orbit just one star in a binary system, staying close enough to their host star that the gravitational influence of the companion star is negligible. These are called S-type orbits, and they can be remarkably stable over billions of years. In other cases, planets orbit both stars in a binary system following P-type, or circumbinary orbits that take them around both stellar components. The famous fictional planet Tatooine from Star Wars, with its double sunset, is actually an example of a circumbinary planet. And remarkably, we've now discovered real planets like this in our galaxy. The Kepler Space Telescope found several circumbinary planets, proving that these exotic worlds actually exist and can remain stable for long periods. The conditions on such planets would be utterly alien compared to Earth. Imagine experiencing seasons not just from your planet's axial tilt, but also from the complex orbital dance of your two parent stars. Sometimes both stars would be visible in the sky simultaneously, creating intense heat and brilliant daylight. At other times, one or both stars might be eclipsed, plunging the planet into unusual periods of dim twilight. The discovery of circumbinary planets has forced astronomers to completely rethink models of planetary formation. How do planets manage to form in the chaotic gravitational environment around binary stars? The answer seems to lie in the same accretion disk processes that we see in single-star systems, but with additional complexities introduced by the gravitational perturbations of the binary stars. These discoveries are expanding our understanding of where life might be able to exist in the universe. Binary star systems are extremely common, perhaps more common than single stars, like our Sun. If planets can form and remain stable in these systems, and if some of those planets can maintain liquid water and other conditions necessary for life, then the number of potentially habitable worlds in our galaxy might be far larger than we previously imagined. The search for life beyond Earth has been revolutionized by our growing understanding of stellar formation and evolution. We now know that the conditions necessary for life depend not just on a planet's distance from its star, but also on the star's age, mass, metallicity, and stellar activity levels. Young stars tend to be very active, producing intense stellar flares and high-energy radiation that could strip away planetary atmospheres. Very old stars might not have enough heavy elements in their planetary systems to support the complex chemistry necessary for life. This has led to the concept of a galactic habitable zone, regions of our galaxy where the conditions are most favorable for the emergence and evolution of life. This zone needs to be far enough from the galactic center to avoid the violent stellar activity and high radiation levels found there, but not so far out that there aren't enough heavy elements to form rocky planets. It also needs to be in a region where the stellar formation history has been conducive to creating stable, long-lived stars like our Sun. Our solar system appears to be located in just such a galactic habitable zone, which might explain why life was able to emerge and evolve on Earth over billions of years. But as our understanding of stellar formation and galactic evolution continues to improve, we're finding that the requirements for habitability might be less restrictive than we once thought. Life, as we're learning, can be remarkably adaptable and might be able to survive in environments that we would have considered completely inhospitable just a few decades ago. The tools and techniques we use to study star formation are advancing at an incredible pace, giving us ever deeper insights into these cosmic processes. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is revealing the hidden details of stellar nurseries that were previously invisible to us. We can now see through the dust and gas that shrouds these regions and watch the star formation process unfold in real time. Ground-based telescopes equipped with adaptive optics can now achieve image quality that rivals or exceeds what we can get from space, while radio telescope arrays like ALMA can map the distribution of molecules in star-forming regions with exquisite detail. Computer simulations have become so sophisticated that we can model the complex physics of stellar formation, from the initial collapse of molecular clouds all the way through to the ignition of nuclear fusion. These advances are revealing that star formation is even more diverse and complex than we ever imagined. Every star-forming region seems to have its own unique characteristics, shaped by local conditions like magnetic field strength, turbulence levels, and the influence of nearby massive stars. Yet, underlying this diversity are universal physical principles that govern how stars form throughout the cosmos. One of the most exciting frontiers in star formation research is the study of the very first stars that formed in the universe. These primordial stars, known as population 3 stars, formed from gas that contained only hydrogen and helium, none of the heavy elements that we see in stars today. Theoretical models suggest that these first stars were likely much more massive than typical stars today, perhaps hundreds of times more massive than our Sun. These stellar giants would have burned through their nuclear fuel incredibly quickly, living for only a few million years before exploding as the most powerful supernova the universe has ever seen. These explosions would have been so energetic that they could have ejected material completely out of the galaxies in which they formed, seeding the intergalactic medium with the first heavy elements and setting the stage for the formation of the next generation of stars. Although we have never directly observed a population 3 star, they all died billions of years ago. We might be getting close. The James Webb Space Telescope is capable of seeing farther back in time than any previous instrument, and it might be able to detect the signatures of these primordial stellar explosions in the most distant galaxies we can observe. Understanding these first stars is crucial for understanding how the universe evolved from its simple post-Big Bang state to the complex, chemically rich cosmos we see today. They represent the beginning of cosmic chemical evolution, the first step in the long chain of stellar birth and death that eventually led to the formation of planets like Earth and the emergence of life. The story of stellar formation is ultimately a story about the universe learning to create complexity from simplicity. What began as a cosmos filled with nothing but hydrogen and helium has evolved into a universe rich with heavy elements, complex molecules, and the potential for life. Every new star that forms continues this ancient process, adding its own contribution to the cosmic symphony of creation and destruction that has been playing for over 13 billion years. As we continue to study these processes, we're not just learning about the physics of how stars form, we're uncovering the fundamental mechanisms that drive cosmic evolution and make life itself possible. The birth of every star is simultaneously an ending and a beginning, a moment when the raw materials of the cosmos are transformed into engines of light and heat that will shine for billions of years, creating the conditions necessary for planets, chemistry, and ultimately, consciousness to emerge. The next time you look up at the night sky, remember that you're seeing the results of this cosmic manufacturing process that has been operating since the dawn of time. Every point of light represents a successful stellar birth, a triumph of gravity and nuclear physics over the cold darkness of space. And somewhere out there, in molecular clouds so distant that their light hasn't yet reached us, new stars are being born right now, continuing the eternal cycle of cosmic creation that connects us to the very origins of the universe itself. The scale of this cosmic manufacturing becomes even more breathtaking when we consider the sheer number of stellar nurseries operating simultaneously throughout our galaxy. Right now, there are approximately 4,000 active star-forming regions in the Milky Way, each one a bustling cosmic maternity ward, where dozens, hundreds, or even thousands of new stars are taking their first breaths. But here's what will absolutely blow your mind about the diversity of these stellar births. Not all stars are created equal, and the type of star that emerges depends entirely on the mass of the original collapsing core. Think of it like cosmic Russian roulette, where the spin of the wheel determines whether you get a stellar lightweight that will burn steadily for trillions of years, or a cosmic heavyweight that will live fast, die young, and go out in the most spectacular explosion the universe has to offer. The smallest stars, called red dwarfs, are the marathon runners of the cosmic world. These stellar minimalists contain less than half the mass of our Sun, but what they lack in size, they make up for in longevity. A red dwarf star will burn hydrogen so slowly and efficiently that it can continue shining for up to 10 trillion years. That's nearly 1,000 times longer than the current age of the universe. To put that in perspective, if a red dwarf star had formed at the moment of the Big Bang, it would still have 99.9% of its fuel remaining today. These cosmic tortoises represent the ultimate in stellar efficiency. They're so good at conserving their hydrogen fuel that they can literally outlive every other type of star in the universe. When the last massive stars have exploded and died, when medium-sized stars like our Sun have swollen into red giants and then faded to white dwarfs, red dwarfs will still be burning bright, the final lighthouses in an increasingly dark cosmos. But the story gets even more fascinating when we consider what happens inside these stellar furnaces. The nuclear fusion reactions that power red dwarfs occur so slowly that they can completely mix their internal contents over time. Unlike larger stars that develop distinct layers and eventually run out of fuel in their cores, red dwarfs can access their entire hydrogen supply, burning every last atom before finally exhausting their nuclear reserves. On the opposite end of the stellar spectrum are the cosmic giants, massive stars with 10, 20, 50, or even 100 times the mass of our Sun. These stellar behemoths are the universe's heavy metal factories, and their lives unfold like cosmic tragedies played out on the grandest possible stage. Where red dwarfs burn their fuel with miserly precision, massive stars consume hydrogen with reckless abandon, burning through their nuclear reserves at rates that would make a gas-guzzling sports car look efficient. The core of a massive star is a nuclear furnace of unimaginable intensity. Temperatures reach hundreds of millions of degrees. Pressures exceed anything we could create on Earth. And the energy output is so enormous that a single massive star can outshine an entire galaxy of smaller stars. The radiation pressure from nuclear fusion is so intense that it's constantly trying to blow the star apart, held in check only by the star's own tremendous gravity. But here's where the physics becomes absolutely mind-bending. As a massive star burns through its hydrogen fuel, it doesn't just fade away like a dying candle. Instead, it begins a cosmic countdown that leads to one of the most violent events in the universe. When the hydrogen in the core is exhausted, the star begins fusing helium into carbon and oxygen. When the helium runs out, it starts fusing carbon into neon and magnesium. This process continues through a series of increasingly rapid burning phases: neon burning, oxygen burning, and finally, silicon burning. Each successive burning phase happens faster than the last, like a cosmic snowball rolling downhill and gathering speed. The hydrogen burning phase might last millions of years, but silicon burning, the final stage, lasts only days or weeks. It's as if the star is racing toward its own destruction, desperately trying to stave off gravitational collapse by burning heavier and heavier elements. The end result of this frantic nuclear burning is the creation of iron in the star's core. And here's where things get truly dramatic, because iron is the ultimate stellar poison. Unlike lighter elements, iron cannot be fused to release energy. It actually absorbs energy when fused. The moment a massive star starts producing iron in significant quantities, its fate is sealed. The nuclear furnace that has been supporting the star against its own gravity suddenly shuts down, and catastrophe follows within seconds. What happens next is one of nature's most spectacular displays of violence and creation rolled into one. With no outward pressure from nuclear fusion to balance gravity's inward pull, the star's core collapses catastrophically. In less than a second, a core the size of Earth is compressed to a sphere only about 12 miles across. The matter becomes so dense that protons and electrons are literally crushed together to form neutrons, creating a city-sized ball of the densest material in the universe. This core collapse releases more energy than our sun will produce over its entire 10 billion year lifetime, and it releases it all in a matter of seconds. The energy is so enormous that it drives a shockwave outward through the star at thousands of miles per second, completely obliterating the star's outer layers in what we call a supernova explosion. But here's the truly beautiful part of this cosmic catastrophe. The temperatures and pressures generated during a supernova are so extreme that they can forge elements that no star could create during its normal lifetime. Gold, platinum, uranium, and dozens of other heavy elements are created in the nuclear cauldron of the explosion, and then scattered throughout space by the blast. This is where the connection to your own existence becomes almost poetic. The gold in your jewelry, the uranium that powers nuclear reactors, the platinum in catalytic converters, all of these elements were forged in the final moments of massive stars and scattered through space by supernova explosions. Every heavy element in your body beyond iron was created not in the steady nuclear burning of a living star, but in the violent death throes of a stellar giant. The shockwaves from these explosions don't just disperse heavy elements. They also trigger the formation of new stars. When a supernova shockwave encounters a nearby molecular cloud, it can compress the gas and dust enough to initiate gravitational collapse. It's like a cosmic domino effect, where the death of one generation of stars triggers the birth of the next. The stellar cycle continues, each generation building on the chemical legacy of those that came before. This brings us to one of the most profound realizations in all of astronomy. The elements that make up your body have been on an incredible journey through space and time. The carbon atoms that form the backbone of your DNA were forged in the cores of massive stars billions of years ago. They were scattered through space by supernova explosions, drifted through the galaxy for millions of years, eventually became part of the molecular cloud that collapsed to form our solar system, condensed into the rocky material that became Earth, and ultimately found their way into the complex organic molecules that make you who you are. You are not just made of stardust. You are made of the ashes of stellar giants, the precious elements created in the universe's most violent events. Every atom in your body is a survivor of cosmic catastrophes that played out on scales of time and space that dwarf human comprehension. The calcium in your bones witnessed the birth and death of stars. The iron in your blood was forged in stellar cores under pressures that could crush entire planets. But the stellar formation story doesn't end with individual stars. Recent discoveries have revealed that stars don't just form randomly throughout space. They organize themselves into hierarchical structures that span incredible scales. Star clusters, containing hundreds or thousands of stars, form within larger associations that can span hundreds of light years. These associations are themselves part of even larger structures called complexes that can contain millions of stars spread across thousands of light years. The Orion Complex, visible as the famous constellation in our winter sky, is a perfect example of this hierarchical organization. What appears to us as a simple pattern of bright stars is actually a vast three-dimensional structure containing multiple star-forming regions at different distances from Earth. The bright stars of Orion's belts, the glowing gas of the Orion Nebula, and the dark dust lanes that thread through the constellation are all part of a single, enormous star formation complex that has been actively creating new stars for millions of years. Within this complex, we can see star formation happening at every scale, there are dense cores just beginning to collapse, protostars surrounded by dusty cocoons, newly ignited stars blowing away their birth material, and fully mature stars that have already settled into stable hydrogen burning. It's like having a cosmic museum of stellar evolution, where every stage of the process is on display simultaneously. These star-forming complexes are shaped by processes that operate on galactic scales. The rotation of our galaxy creates spiral density waves that sweep through the Milky Way's disk, compressing gas and dust and triggering episodes of enhanced star formation. The gravity of neighboring galaxies can distort our galaxy's shape, creating tidal streams of material that can also trigger stellar birth. Even the supermassive black hole at our galaxy's center influences star formation through its powerful gravitational field and the high-energy jets it occasionally produces. What's emerging from all these observations is a picture of star formation as a truly cosmic phenomenon. Not just isolated events happening in distant nebulae, but part of a vast, interconnected web of processes that spans from the smallest molecular cores to the largest galactic structures. The birth of every star is connected to the deaths of previous generations, to the chemical evolution of galaxies, and to the fundamental forces that govern the universe itself. This cosmic perspective on stellar birth has profound implications for our understanding of life in the universe. If star formation is so intimately connected to galactic evolution and chemical enrichment, then the emergence of planets and potentially life depends on billions of years of stellar recycling. The first stars that formed after the Big Bang could never have hosted Earth-like planets because the heavy elements necessary for rocky worlds simply didn't exist yet. It took multiple generations of stellar birth, evolution, and death to enrich the galaxy with enough carbon, oxygen, silicon, iron, and other heavy elements to make terrestrial planets possible. This means that life as we know it could only emerge after the universe had aged enough for this cosmic chemical evolution to run its course. We are living in what might be the first epoch of cosmic history, when complex life is even possible. The timing of this cosmic chemical evolution also suggests something remarkable about the future of life in the universe. If we're living near the beginning of the era when complex life is possible, then the vast majority of potentially habitable worlds may still be forming. The universe might be on the verge of a biological explosion that will dwarf anything we can currently imagine, as billions of new planetary systems form around metal-rich stars throughout the galaxy. But there's another side to this cosmic story that's equally fascinating. The same processes that create the heavy elements necessary for life also determine when and where life might be able to survive. The violent environments around massive star-forming regions, with their intense radiation and frequent supernova explosions, could be hazardous to any nearby planets. The galactic habitable zone, the region where conditions are most favorable for life, depends on a delicate balance between having enough heavy elements to form planets, while avoiding the most violent stellar neighborhoods. Our solar system appears to occupy a particularly favorable location in this galactic habitable zone. We're far enough from the galaxy's center to avoid the chaotic environment near the supermassive black hole, but close enough to benefit from billions of years of chemical enrichment by previous generations of stars. We're also located between spiral arms in a relatively quiet region where the rate of nearby supernova explosions is lower than average. This cosmic real estate perspective on habitability is changing how we think about the search for life beyond Earth. Instead of just looking for planets in the habitable zones around individual stars, we're beginning to consider the galactic context, where the potential host stars are located in regions of the galaxy where life could survive and evolve over billions of years. The search for potentially habitable exoplanets has been revolutionized by our growing understanding of stellar formation and evolution. We now know that the characteristics of a star, its mass, age, metallicity, and activity level, are crucial factors in determining whether its planets could support life. Young stars tend to be highly active, producing intense flares and high-energy radiation that could strip away planetary atmospheres. Very low-mass stars might tidally lock their planets, creating permanent day and night sides with extreme temperature differences. But perhaps most importantly, we're learning that the formation of planetary systems is intimately connected to the star formation process itself. The dusty disks that surround young stars, the same disks from which planets form, are shaped by the complex interplay of gravity, magnetic fields, and stellar radiation. Understanding how these protoplanetary disks evolve gives us crucial insights into how planetary systems like our own came to be. Recent observations with telescopes like ALMA have revealed that protoplanetary disks are far more complex and dynamic than we ever imagined. They contain intricate structures, gaps, rings, spirals, and asymmetries that are carved by the gravitational influence of forming planets. We can literally watch planetary systems being born, seeing how the same processes that created our solar system are playing out around other stars throughout the galaxy. These observations are revealing that planetary formation is a remarkably common outcome of the star formation process. Nearly every star appears to form with a disk of surrounding material, and most of these disks show evidence of planet formation. This suggests that planetary systems might be the norm rather than the exception in our galaxy. A profound shift from the view that prevailed just a few decades ago, when our solar system was thought to be unique, or at least highly unusual. The diversity of planetary systems we're discovering is staggering. Some contain multiple giant planets orbiting close to their stars. Others have Earth-sized worlds in tight orbits that complete their years in just a few days. Some systems have planets with highly eccentric orbits that take them from scorching heat to frigid cold during each orbital cycle. This diversity is teaching us that the formation of our own solar system, with its orderly arrangement of terrestrial planets close to the Sun and gas giants farther out, might be just one of many possible outcomes. But amid all this diversity, we're beginning to identify patterns that might help us understand which types of planetary systems are most likely to host life. Systems with multiple planets in stable, nearly circular orbits seem to be more conducive to long-term habitability than those with highly eccentric or chaotic orbits. Stars with intermediate metallicities, not too metal poor to form substantial planets, but not so metal rich that they form only gas giants, might be the sweet spot for terrestrial planet formation. The chemical composition of stellar nurseries is also proving to be crucial of detected in star-forming regions, including complex carbon, for understanding where life might emerge. The organic molecules that we chemistry suggest that the raw materials for life are based compounds that are precursors to biological being distributed throughout planetary systems during their formation. This means that this cosmic perspective on life, both hum worlds might come preloaded with some of the chemical ingredients necessary for the emergence of life. The implications of bling and inspiring, humbling, because they reveal just how many cosmic coincidences had to align for our existence to be possible. From the formation of the first stars that created heavy elements, to the particular location of our solar system in the galaxy, to the specific timing of our planet's formation in the era when complex chemistry was finally possible. But they're also inspiring because they suggest that life might be far more common than we ever dared to hope. If the ingredients for life are natural byproducts of stellar formation, might be living in a universe that's, if planetary systems are the normal outcome of stellar with potentially habitable worlds, then we birth. And if the galaxy is Phil imagine, the story of stellar birth teeming with life in forms we can barely is ultimately a story of cosmic evolution, of how the universe has transformed itself from a simple collection of hydrogen and helium into a complex, chemically rich cosmos capable of supporting planets, chemistry, and life itself. Every new star that forms continues this ancient process of cosmic self-transformation, adding its own chapter to a story that has been unfolding for over 13 billion years. And perhaps the most remarkable aspect of this cosmic story is that it's still being written. Right now, as you're contemplating these ideas, new stars are igniting throughout the galaxy. New planetary systems are forming around young stars. New organic molecules are being synthesized in the cold depths of molecular clouds. The universe is still actively creating the conditions for new forms of complexity and are living witnesses to this ongoing cosmic creativity, life to emerge. We, temporary arrangements of stellar material that have achieved the remarkable ability to contemplate the very processes that brought us into existence. When we study star formation, we're not just learning about distant astronomical phenomena. We're uncovering the fundamental mechanisms that made our own existence possible and that continue to shape the cosmic environment in which we live. The next phase of stellar formation research promises to be even more exciting than what we've discovered so far. The James Webb Space Telescope is revealing the birth of stars with unprecedented clarity, showing us details of the formation process that were completely hidden from previous generations of astronomers. Future space missions will be able to directly image the atmospheres of potentially habitable exoplanets, searching for the chemical signatures that might indicate the presence of life. Ground-based telescopes are becoming so sophisticated that they can now detect the subtle gravitational wobbles caused by Earth-sized planets around nearby stars. Radio telescope arrays can map the distribution of organic molecules in star-forming regions with exquisite precision, and computer simulations are becoming so detailed that we can model the entire process of stellar and planetary formation from first principles, predicting what we should see and testing our theories against observations. All of these advances are converging toward a deeper understanding of our place in the cosmic story of stellar birth and death. We're beginning to see how the formation of stars, planets, and life are all connected parts of a single, grand narrative of cosmic evolution. A story that began with the first stars lighting up the primordial universe and continues today with the ongoing birth of new stellar generations throughout our galaxy. As we stand at this cosmic crossroads, watching new generations of stars being born across our galaxy, we're witnessing something that challenges everything we thought we knew about the nature of stellar formation itself. Because here's what recent discoveries have revealed that will completely blow your mind. The process of starbirth isn't just happening in isolation. It's part of a vast cosmic network, where stellar nurseries actually communicate with each other across hundreds of light years of space. Think about this for a moment. When a massive star explodes as a supernova in one region of the galaxy, the shockwave doesn't just disperse heavy elements randomly into space, it creates expanding bubbles of hot gas that can travel for millions of years, eventually encountering other molecular clouds and triggering new episodes of star formation. It's like a cosmic chain reaction where the death of stars in one location directly influences the birth of stars in completely different regions of the galaxy. But the story gets even more extraordinary when we consider the role of galactic magnetic fields in orchestrating this stellar symphony. These invisible force lines, stretching across thousands of light years, act like cosmic highways that channel gas and dust towards specific locations where conditions are optimal for star formation. The magnetic fields don't just guide material, they actually regulate the entire process, controlling how quickly stars form and determining which regions of the galaxy will become the next stellar birthplaces. Recent observations have revealed that these magnetic highways are incredibly complex, forming intricate networks that connect star-forming regions across vast distances. When material flows along these magnetic field lines, it carries with it the chemical signatures of previous generations of stellar death and birth. This means that every new star that forms inherits not just the raw materials from its immediate surroundings, but also the accumulated chemical history of stellar evolution from across the galaxy. This galactic-scale organization of star formation has profound implications for understanding how chemical elements are distributed throughout the Milky Way. Instead of heavy elements being randomly scattered by supernova explosions, they're systematically transported along magnetic field lines to regions where they can be incorporated into new stars and planetary systems. It's like the galaxy has its own circulatory system, pumping the products of stellar evolution to where they're needed most. The precision of this cosmic distribution system is absolutely mind-boggling. Computer simulations show that the magnetic field structure of our galaxy has been shaped by billions of years of stellar feedback, creating pathways that optimize the delivery of heavy elements to star-forming regions. The galaxy has essentially evolved its own logistics network for stellar manufacturing, ensuring that each new generation of stars has access to the chemical ingredients created by their predecessors. But here's where things get truly fascinating from a temporal perspective. The light we see from distant star-forming regions represents snapshots of stellar birth taken at different moments in cosmic history. When we observe a stellar nursery located 10,000 light-years away, we're seeing star formation as it was happening 10,000 years ago. This means we can actually watch the evolution of stellar birth processes by comparing observations of star-forming regions at different distances. What these observations reveal is that star formation has been accelerating throughout cosmic history. The early universe formed stars much more slowly than we see today, partly because there were fewer heavy elements available to facilitate the cooling and collapse of gas clouds. As successive generations of stars enriched the galaxy with heavier elements, the efficiency of star formation increased dramatically. We're living in an era of unprecedented stellar productivity, when new stars are being born at rates that dwarf anything the universe experienced in its youth. This acceleration of stellar birth has created what astronomers call the cosmic noon period, an epoch roughly 10 billion years ago when star formation reached its peak throughout the universe. During this golden age of stellar creation, galaxies were forming stars at rates 10 times higher than we see today. The universe was literally blazing with the light of newborn stars, creating a cosmic fireworks display on scales that make our current era seem relatively quiet by comparison. But the cosmic noon period wasn't just about quantity. It was also when the universe developed the sophisticated stellar formation mechanisms we observe today. The feedback processes that regulate star formation, the magnetic field structures that channel material, and the chemical enrichment cycles that optimize stellar birth all reach maturity during this crucial epoch. In a sense, the universe learned how to make stars more efficiently through billions of years of trial and error. Understanding this cosmic evolution of stellar formation is crucial for predicting the future of star birth in our galaxy and others. Current observations suggest that we're now in a declining phase of cosmic star formation, with the overall rate of stellar birth dropping as the universe ages and available gas supplies become depleted. But this decline isn't uniform. Some regions of galaxies are still experiencing intense bursts of stellar creation, while others have essentially shut down their star-forming factories. The Milky Way itself is experiencing this transition from active to declining star formation. Our galaxy is currently forming new stars at a rate of about 1 solar mass per year, a respectable pace, but much slower than during the cosmic noon period when our galaxy was creating stars 10 times faster. This gradual decline is partly due to the depletion of available gas, but it's also influenced by the increasing efficiency of stellar feedback in preventing new star formation. As massive stars have become more common in our galaxy's history, their powerful winds and supernova explosions have become increasingly effective at heating and dispersing the gas that would otherwise collapse to form new stars. It's a self-limiting process where successful star formation actually inhibits future stellar birth by changing the physical conditions in molecular clouds. This cosmic aging process raises fascinating questions about the long-term future of stellar formation. Will our galaxy eventually exhaust its supply of star-forming material, leading to a gradual fade into darkness as existing stars burn out? Or will new mechanisms emerge to rejuvenate the stellar birth process, perhaps through interactions with neighboring galaxies or the accretion of fresh gas from intergalactic space? Recent observations suggest that galaxy collisions and mergers play a crucial role in triggering new episodes of intense star formation. When galaxies interact gravitationally, their gas supplies can be compressed and stirred, leading to spectacular starbursts that can create millions of new stars in just a few million years. Our own Milky Way is destined to collide with the Andromeda Galaxy in about 4.5 billion years, an event that will likely trigger a massive burst of stellar creation throughout both galaxies. But even without such dramatic interactions, the process of stellar formation continues to evolve and adapt. Astronomers are discovering new types of stellar nurseries that operate according to different physical principles than the classical molecular cloud collapse we've discussed. Some stars appear to form through the fragmentation of massive gas streams that flow along cosmic web filaments, while others emerge from the collision and merger of smaller gas clumps. These diverse formation mechanisms suggest that the universe has developed multiple pathways for creating stars, ensuring that stellar birth can continue even as traditional star-forming environments become less common. It's like biological evolution, developing different survival strategies. The cosmos has found numerous ways to maintain the stellar creation process under changing galactic conditions. One of the most exciting recent discoveries involves what astronomers call runaway star formation. Episodes where the normal regulatory mechanisms break down and stars form at rates that seem almost impossibly fast. These stellar baby booms can create thousands of massive stars in regions of space that would normally produce only a few dozen stellar births. The physics behind these extreme formation events is still being studied, but they appear to involve the rapid collapse of unusually massive and dense gas concentrations. These runaway star formation episodes have profound consequences for galactic evolution because they can dramatically alter the chemical composition and structure of entire galactic regions in just a few million years. The combined energy output from thousands of massive stars can create super bubbles of hot gas that extend for thousands of light years, fundamentally reshaping the interstellar medium and influencing star formation patterns for millions of years to come. But perhaps the most mind-bending aspect of these discoveries is what they reveal about the relationship between stellar formation and the large-scale structure of the universe itself. The cosmic web, that vast network of dark matter filaments that connects galaxies across billions of light years, appears to play a direct role in channeling gas towards star-forming regions. Galaxy mergers, which trigger intense starbursts, are themselves orchestrated by the gravitational influence of dark matter structures that span cosmic scales. This means that the birth of individual stars is ultimately connected to the evolution of the universe's largest structures. When you look up at a newly formed star in the night sky, you're seeing the end results of processes that began with quantum fluctuations in the early universe, evolved through billions of years of cosmic structure formation, and culminated in the gravitational collapse of a molecular cloud in our local galactic neighborhood. The interconnectedness of these cosmic processes is so profound that some astronomers have begun to think of star formation not as isolated events, but as manifestations of the universe's ongoing self-organization. Each stellar birth represents a moment when cosmic evolution achieves a new level of complexity, creating nuclear furnaces that will eventually produce the heavy elements necessary for the next phase of cosmic development. This perspective transforms our understanding of what it means to witness stellar birth. When we observe a star-forming region through our telescopes, we're not just seeing a local astronomical phenomenon, we're glimpsing the universe in the act of creating its own future. Every new star represents new possibilities for planetary formation, chemical evolution, and potentially even the emergence of life itself. The technology that allows us to study these cosmic birth processes continues to advance at a breathtaking pace. The James Webb Space Telescope can now peer through the dusty cocoons that shroud forming stars, revealing details of the formation process that were completely hidden just a few years ago. We can see individual protostellar jets carving through molecular clouds, watch as stellar winds clear cavities around newborn stars, and observe the formation of protoplanetary disks where future worlds will take shape. Ground-based telescopes equipped with adaptive optics can now achieve image resolution that approaches the theoretical limits imposed by the laws of physics. Radio telescope arrays can map the distribution of molecules in star-forming regions with precision that allows us to trace the flow of material as it falls toward forming stars. And computer simulations have become so sophisticated that we can model the entire stellar formation process, from the initial turbulence in molecular clouds all the way through to the ignition of nuclear fusion. These technological advances are revealing that stellar formation is even more complex and beautiful than we ever imagined. Every star-forming region has its own unique characteristics, shaped by the specific combination of magnetic fields, turbulence, stellar feedback, and chemical composition that exists in that particular location. Yet underlying this diversity are universal physical principles that govern how matter organizes itself into stars throughout the cosmos. The diversity of stellar formation environments also means that different types of stars preferentially form under different conditions. Massive stars tend to form in the densest, most turbulent regions of molecular clouds, where the rapid collapse can overcome the intense radiation pressure that would otherwise prevent such large objects from forming. Smaller stars like red dwarfs can form in more quiescent environments, slowly accumulating mass over extended periods. This environmental dependence of stellar formation has important implications for understanding the distribution of different stellar types throughout our galaxy. The central regions, where gas densities are higher and stellar feedback is more intense, tend to produce more massive stars. The outer regions, where conditions are more peaceful, are better suited for forming the low-mass stars that will outlive all other stellar types. These galactic gradients in stellar formation create a complex ecology where different regions of our galaxy host different stellar populations with different characteristics and evolutionary histories. The solar neighborhood, located in the galactic suburbs between spiral arms, represents a relatively calm environment that has been conducive to forming stable, long-lived stars like our Sun. But even within our local galactic neighborhood, the stellar formation process continues to surprise us with its complexity and beauty. Recent observations have revealed that many of the molecular clouds in our vicinity are threaded with intricate networks of magnetic field lines that create stunning geometric patterns visible in polarized light. These magnetic structures guide the flow of material during stellar formation, creating spiral patterns, hourglass shapes, and other elegant configurations that demonstrate the fundamental role of magnetism in cosmic organization. The interplay between gravity, magnetic fields, and turbulence in these molecular clouds creates a form of cosmic choreography where matter flows along invisible pathways toward regions where new stars will be born. It's like watching an elaborate three-dimensional dance performed by gas and dust particles, guided by forces that operate on scales ranging from individual stellar systems to entire galactic regions. Understanding this cosmic choreography is crucial for predicting where and when new stars will form in our galaxy. Astronomers are developing increasingly sophisticated models that can forecast stellar formation rates based on the distribution of gas, the strength of magnetic fields, and the influence of stellar feedback from previous generations of stars. These predictive models are revealing that stellar formation follows cyclical patterns, with periods of enhanced activity followed by quiescent phases as feedback processes regulate the birth of new stars. The cyclical nature of stellar formation has profound implications for the long-term evolution of our galaxy and others. Rather than steadily declining toward a dark future as gas supplies are exhausted, galaxies may experience periodic rejuvenation as new gas is accreted from intergalactic space, or as interactions with neighboring galaxies trigger fresh episodes of stellar birth. This dynamic view of galactic evolution suggests that the universe's stellar formation story is far from over. We may be living through a temporary lull in cosmic star formation, but future epochs could see dramatic revivals of stellar birth as galaxies evolve, interact, and continue to organize matter into ever more complex configurations. The ultimate fate of stellar formation in our universe depends on fundamental questions about cosmic evolution that we're only beginning to answer. Will the accelerating expansion of space eventually prevent new gas from falling into galaxies, shutting down stellar formation permanently? Or will quantum fluctuations in the vacuum of space continue to create new matter, providing fuel for stellar birth even in the far future? These questions push us toward the very frontiers of physics and cosmology, where our understanding of stellar formation connects to the deepest mysteries about the nature of space, time, and matter itself. The same quantum mechanical processes that govern nuclear fusion in stellar cores may also determine the ultimate fate of the universe and whether new stars will continue to be born in the distant future. As we continue to explore these cosmic mysteries, we're discovering that the story of stellar birth is ultimately the story of how the universe creates complexity from simplicity, organization from chaos, and light from darkness. Every new star that ignites represents a victory of structure over entropy, a triumph of gravitational organization over the random motions of gas particles in space. The birth of stars is thus not just an astronomical phenomenon, but a manifestation of the universe's fundamental creativity, its ability to transform simple ingredients into complex systems capable of producing heavy elements, planetary systems, and potentially even life itself. When we study stellar formation, we're investigating the cosmic mechanisms that make complexity and consciousness possible in our universe. This perspective elevates the study of stellar birth from a specialized field of astronomy to a fundamental investigation of how the universe works at its deepest levels. The nuclear physics that powers stellar cores, the gravitational dynamics that shape molecular clouds, and the magnetic processes that guide stellar formation are all expressions of the same underlying physical principles that govern reality at every scale. Understanding these principles through the lens of stellar formation gives us insights that extend far beyond astronomy. The same physics that explains how stars form also governs the behavior of matter under extreme conditions, the evolution of complex systems, and the emergence of order from apparent chaos. Stellar nurseries serve as natural laboratories where we can study physics under conditions that we could never replicate on Earth. The knowledge gained from studying stellar formation has already led to advances in plasma physics, magnetic field theory, and our understanding of how complex systems self-organize. These insights have practical applications in fields ranging from fusion energy research to the development of advanced materials with novel properties. But perhaps the most profound impact of stellar formation research lies in how it changes our perspective on our place in the cosmic order. When we realize that the atoms in our bodies were forged in stellar cores, that the planets in our solar system formed from the debris of stellar death and birth, and that the ongoing process of stellar formation continues to shape the galaxy we inhabit, we begin to see ourselves not as separate from the cosmos, but as integral parts of its ongoing evolution. This cosmic perspective has the power to transform how we think about our responsibilities as conscious beings in an evolving universe. We are not just observers of cosmic processes, but participants in them, temporary arrangements of stellar material that have achieved the remarkable ability to study and understand the very processes that brought us into existence. The story of stellar formation thus becomes a story about cosmic self-awareness, about how the universe has evolved to the point where it can study itself through conscious beings like us. When we point our telescopes at distant star-forming regions, we are literally the cosmos examining its own creative processes, trying to understand how it continues to generate the complexity and beauty we observe throughout space and time. This reflexive quality of cosmic investigation, the universe studying itself through conscious observers, suggests that the emergence of intelligence and scientific understanding may be as fundamental to cosmic evolution as the formation of stars and galaxies themselves. We may be witnessing not just the physical evolution of the universe, but its intellectual and spiritual evolution as well, as matter organized into conscious forms begins to comprehend the magnificent processes that govern cosmic development. The future of stellar formation research promises to deepen this cosmic self-understanding even further. As our observational capabilities continue to advance and our theoretical models become more sophisticated, we will gain increasingly detailed insights into how stars form, how they influence their environments, and how they contribute to the ongoing evolution of cosmic complexity. These advances will not only satisfy our scientific curiosity about stellar formation processes, but will also provide crucial information for understanding the potential for life throughout the universe. By learning how stars and planetary systems form under different conditions, we can better predict where habitable worlds might exist and what factors are most important for the emergence and evolution of life. The search for life beyond Earth is thus intimately connected to our understanding of stellar formation. Every discovery about how stars are born brings us closer to answering the fundamental question of whether we are alone in the universe or part of a cosmic community of conscious beings that has emerged from the same stellar formation processes we observe throughout space. As we stand on the threshold of these great discoveries, contemplating the magnificent stellar nurseries that continue to birth new suns throughout our galaxy, we are reminded that we are living witnesses to one of the universe's most fundamental and beautiful processes. The birth of every star is a cosmic celebration, a moment when matter achieves a new level of organization and begins its journey toward creating the complexity that makes planets, chemistry, and consciousness possible. Tonight, we stand at the threshold of something even more extraordinary about stellar birth that challenges everything we thought we understood about the very nature of time itself in these cosmic nurseries. Because here's what recent discoveries have revealed that will fundamentally alter how you think about stellar formation. Time doesn't flow uniformly throughout these star-forming regions. In the densest cores where protostars are condensing, gravitational time dilation means that time literally moves slower than in the surrounding molecular cloud. Picture this cosmic phenomenon unfolding before your eyes. As matter spirals inward toward a forming protostar, it's not just experiencing increasing temperatures and pressures, it's actually entering a region where the flow of time itself begins to stretch and warp. Einstein's theories predicted this effect, but only now are we beginning to understand how profoundly it shapes the stellar birth process. What this means is absolutely mind-bending. Events that take thousands of years to unfold in the outer regions of a molecular cloud might take tens of thousands of years to complete near the dense core of a forming star. It's as if the universe has created natural time machines in these stellar nurseries, where different regions experience the passage of time at fundamentally different rates. This temporal complexity adds layers of richness to stellar formation that we never anticipated. When we observe a star-forming region, we're not just seeing different spatial scales of the same process, we're witnessing events that are literally happening at different rates of time. The outer envelope of a molecular cloud might complete several cycles of compression and expansion, while the inner core experiences only a single gravitational oscillation. But here's where this temporal distortion becomes truly fascinating from an evolutionary perspective. The time dilation effects in stellar formation regions mean that the nuclear physics happening in protostellar cores occurs in a different temporal framework than the chemistry happening in the surrounding gas and dust. Complex organic molecules forming on dust grain surfaces experience time at one rate, while the nuclear reactions beginning to ignite in stellar cores experience time at another rate entirely. This creates a form of temporal layering in stellar formation that we're only beginning to appreciate. The same physical region of space contains multiple time streams, each flowing at different rates depending on the local gravitational field strength. It's like watching a cosmic symphony where different instruments are playing at different tempos, yet somehow the overall composition maintains perfect harmony. The implications of this temporal complexity extend to how we understand the relationship between stellar formation and planetary system development. The protoplanetary disks that form around young stars exist in gravitational fields that are strong enough to create measurable time dilation effects. This means that the process of planetary formation, the gradual accumulation of dust into pebbles, pebbles into planetesimals, and planetesimals into full-sized worlds, occurs in a temporal environment that's fundamentally different from the surrounding interstellar medium. Consider what this means for the chemical evolution that occurs during planetary formation. The complex organic chemistry happening in protoplanetary disks unfolds in regions where time moves differently than in the molecular clouds from which the raw materials originated. Reaction rates, molecular diffusion, and the formation of increasingly complex compounds all occur within this altered temporal framework. This temporal stratification might actually be crucial for enabling the level of chemical complexity necessary for life to emerge. The slightly slower passage of time in the dense regions of protoplanetary disks could provide the extended reaction times necessary for particularly complex organic synthesis to occur. Molecules that would be unstable or short-lived in the normal interstellar medium might have the time they need to form and persist in these temporally dilated environments. Recent computational models of stellar formation are beginning to incorporate these relativistic effects, and the results are revealing new subtleties in how stars are born. The accretion of material onto forming protostars doesn't happen at a constant rate as previously assumed, but varies depending on the temporal gradients established by gravitational time dilation. Material falling from regions where time moves faster encounters the slower temporal environment near the protostar, creating complex dynamics that influence the final mass and characteristics of the resulting star. These temporal effects also help explain some of the puzzling observations we've made about the variability of young stellar objects. Protostars often exhibit irregular brightness fluctuations and episodic mass accretion events that seemed random until we began to understand the role of gravitational time dilation in stellar formation. What appears as chaotic variability from our external perspective might actually be highly organized processes unfolding according to different temporal rhythms in different regions of the forming stellar system. The magnetic field structures that thread through star-forming regions add another layer of complexity to this temporal tapestry. Magnetic field lines themselves can become stretched and distorted by gravitational time dilation effects, creating configurations that wouldn't be possible in uniform space-time. These warped magnetic structures influence how material flows toward forming stars, creating spiral patterns and jet formations that reflect the underlying temporal geometry of the stellar nursery. But perhaps the most profound implication of these temporal effects involves how we think about the information flow during stellar formation. In regions where time dilation is significant, cause and effect relationships become more complex than simple linear sequences. Events that appear simultaneous from one reference frame might be separated by substantial time intervals when viewed from another perspective within the same star-forming region. This temporal complexity suggests that stellar formation might involve information processing capabilities that we haven't fully recognized. The gravitational fields that create time dilation also influence how information propagates through the forming stellar system. Pressure waves, magnetic disturbances, and chemical gradients all carry information about conditions in different parts of the system, but this information travels through regions where time itself is flowing at different rates. The result is a form of cosmic information processing, where data about stellar formation conditions gets temporally filtered and transformed as it propagates through the system. This might help explain how stellar formation can be simultaneously chaotic on small scales, yet highly organized on larger scales. The temporal filtering effects naturally smooth out rapid fluctuations while preserving longer-term trends and patterns. Understanding these information flow patterns in stellar formation has practical implications for how we interpret observations of star-forming regions. When we see coordinated behavior across large scales in molecular clouds, such as the synchronized formation of multiple protostars or the coherent structure of stellar jets, we might be witnessing the effects of information that has been processed through these complex temporal gradients. The study of temporal effects in stellar formation also connects to some of the deepest questions in physics about the nature of time and causality. Stellar nurseries provide natural laboratories where we can study how time behaves under conditions of strong gravitational fields and complex matter distributions. The insights gained from this research might eventually contribute to our understanding of fundamental physics, including questions about the nature of space-time itself. Recent observations using gravitational wave detectors have begun to reveal another aspect of temporal complexity in stellar formation. The coalescence of binary protostars, a process that can occur when molecular cloud cores fragment into multiple objects, creates ripples in space-time that carry information about the temporal dynamics of the formation process. These gravitational waves provide a completely new window into how time flows during the most dynamic phases of stellar birth. The gravitational wave signatures from stellar formation events are incredibly subtle compared to those from black hole mergers or neutron star collisions, but they contain unique information about the temporal structure of the formation process. By analyzing these signals, astronomers are beginning to reconstruct the detailed timeline of how individual stellar systems came together, including the role of temporal gradients in shaping the final outcomes. This gravitational wave archaeology of stellar formation is revealing that the birth of stars involves far more temporal complexity than we ever suspected. Each stellar formation event creates its own unique space-time signature, a gravitational fingerprint that encodes information about how matter, energy, and time interacted during the crucial phases of stellar birth. The implications extend beyond individual stellar formation events to the evolution of entire star-forming regions. As multiple protostars form within the same molecular cloud, their overlapping gravitational fields create interference patterns in the flow of time itself. These temporal interference effects influence how subsequent generations of stars form within the same region, creating a form of gravitational memory that persists long after the original protostars have evolved into main sequence stars. This gravitational memory helps explain the remarkable organization we observe in stellar associations and clusters. The spatial patterns and velocity structures of stellar groups reflect not just their initial formation conditions, but also the temporal dynamics that governed their birth. Stars that formed in regions of enhanced time dilation retain subtle kinematic signatures that can be detected billions of years later, providing clues about the temporal environment of their formation. The discovery of these temporal effects in stellar formation is also changing how we think about the relationship between stellar birth and galactic evolution. The spiral density waves that trigger star formation throughout galactic disks don't just compress gas and dust, they also create traveling patterns of gravitational time dilation that influence how stellar formation unfolds. These temporal waves add another layer of complexity to the already intricate dynamics of galactic star formation. As spiral density waves sweep through galactic disks, they create regions where the temporal flow is temporarily altered by the enhanced gravitational fields of compressed matter. Star formation that occurs within these temporal anomalies proceeds according to different timescales than formation in more typical galactic environments. This might help explain why stars formed in spiral arms often have different characteristics than those formed in inter-arm regions. The temporal complexity of stellar formation also has profound implications for understanding how the chemical elements created in stellar cores are distributed throughout the galaxy. Supernova explosions that occur in regions of significant time dilation will disperse heavy elements according to temporal dynamics that differ from those in normal space-time. This could create chemical gradients and abundance patterns throughout the galaxy that reflect the temporal history of stellar formation rather than just the spatial distribution of stellar births and deaths. Understanding these temporal chemical distribution patterns is crucial for interpreting the chemical evolution of galaxies and predicting where conditions might be most favorable for the formation of planetary systems capable of supporting life. The heavy elements necessary for rocky planet formation and complex chemistry might be preferentially delivered to regions where temporal conditions are optimal for the development of complex molecular structures. The role of temporal effects in stellar formation becomes even more intriguing when we consider how they might influence the formation of the most massive stars in the universe. These stellar giants form under such extreme gravitational conditions that relativistic effects become unavoidable. The time dilation experienced in the cores of forming massive stars might actually be necessary for enabling the complex nuclear processes that allow these objects to achieve their enormous masses without becoming unstable. The most massive protostars experience gravitational fields so intense that the flow of time in their cores is measurably different from the surrounding environment. This temporal gradient affects how nuclear reactions proceed during the final phases of stellar formation, potentially allowing massive stars to accumulate more material than would be possible under uniform temporal conditions. The universe might have evolved this temporal mechanism specifically to enable the formation of the massive stars that serve as the primary factories for heavy element production. These massive stellar factories operate according to temporal dynamics that are fundamentally different from smaller stars like our Sun. The nuclear fusion processes that power them unfold in environments where time dilation effects influence reaction rates, energy transport, and the overall stellar evolution. Understanding these temporal dynamics is crucial for predicting how massive stars will evolve and what elements they will produce during their lifetimes. The connection between temporal effects and heavy element production in massive stars has implications that extend throughout cosmic history. The first generation of stars that formed after the Big Bang experienced temporal dynamics that were different from modern star formation because the universe itself was denser and more compact. These primordial temporal conditions might have influenced how the first heavy elements were created and distributed, setting the stage for all subsequent stellar and planetary formation. As we trace the temporal evolution of stellar formation from the earliest epochs of cosmic history to the present day, we're uncovering a story of increasing temporal complexity. The universe has evolved not just in terms of its chemical composition and large-scale structure, but also in terms of the temporal dynamics that govern how matter organizes itself into stars and planetary systems. This temporal evolution of stellar formation processes suggests that the universe is becoming increasingly sophisticated in its ability to create complex structures. The temporal gradients and gravitational time dilation effects that we observe in modern stellar nurseries represent billions of years of cosmic evolution toward more intricate and nuanced formation mechanisms. The future of stellar formation might involve even more complex temporal dynamics as the universe continues to evolve and mature. As galaxies merge and interact, they create gravitational environments with temporal characteristics that have never existed before in cosmic history. These novel temporal conditions could enable new types of stellar formation processes that produce stars and planetary systems with properties we haven't yet observed. Understanding the temporal aspects of stellar formation is thus not just about comprehending current astronomical phenomena, but about predicting the future evolution of cosmic structure and the potential for new forms of complexity to emerge. The universe's growing mastery of temporal dynamics in stellar formation might be preparing the stage for even more remarkable developments in cosmic evolution that we can barely imagine. As we continue to explore these temporal frontiers of stellar formation, we're discovering that the birth of stars is far more than just the gravitational collapse of gas and dust. It's a complex dance between matter, energy, space, and time itself. A cosmic choreography that reveals the universe's most fundamental creative processes at work. The realization that time itself is an active participant in stellar formation transforms our understanding of what it means to witness the birth of a star. When we observe these cosmic nurseries, we're not just seeing matter organizing itself into new configurations. We're witnessing the universe experimenting with time itself, exploring how temporal dynamics can be harnessed to create increasingly complex and beautiful structures. This temporal creativity in stellar formation connects to some of the deepest questions about the nature of reality and our place within it. If the universe can manipulate time to facilitate the birth of stars, what other temporal phenomena might be operating on scales we haven't yet recognized? How might the temporal dynamics of stellar formation connect to the emergence of life and consciousness throughout the cosmos? These questions push us toward new frontiers of understanding that blur the boundaries between physics, philosophy, and our deepest sense of wonder about the nature of existence itself. The temporal complexity of stellar formation reminds us that the universe is far stranger and more creative than we ever dared imagine. A cosmic system capable of not just organizing matter and energy, but of orchestrating time itself in service of creating the stars that light up the darkness. and make all higher forms of complexity possible. The journey into understanding temporal effects in stellar formation has revealed that we are living in a universe where time is not just a passive backdrop against which events unfold, but an active participant in the cosmic creative process. Every star that is born represents a triumph of temporal engineering on cosmic scales. A moment when the universe successfully coordinates matter, energy, and time itself to ignite a new nuclear furnace that will burn for millions or billions of years. As we contemplate these temporal mysteries of stellar birth, we find ourselves confronting the extraordinary possibility that consciousness itself might be connected to these temporal dynamics in ways we're only beginning to understand. The complex information processing that occurs in stellar formation regions, mediated by gravitational time dilation and temporal gradients, suggests that the universe might possess forms of temporal intelligence that operate on scales far beyond human comprehension. When we study stellar formation, we might thus be investigating not just the physical processes that create stars, but the temporal mechanisms through which the universe develops increasingly sophisticated forms of organization and complexity. The birth of every star becomes a moment of cosmic learning, an experiment in temporal dynamics that contributes to the universe's growing mastery of creative processes. This perspective elevates stellar formation from an astronomical phenomenon to a window into the universe's deepest creative principles. Principles that govern not just the birth of stars, but potentially the emergence of all complex structures throughout cosmic history, including the temporal dynamics that made the evolution of life and consciousness possible on worlds like our own. Tonight, as you contemplate the extraordinary temporal complexities we've explored, there's one final revelation about stellar formation that will forever change how you perceive every point of light scattered across the night sky. Because what we're discovering is that the birth of stars isn't just creating nuclear furnaces. It's creating the fundamental architecture of consciousness itself throughout the cosmos. Here's what will absolutely stagger you. The same gravitational time dilation effects that govern stellar formation also create the precise temporal conditions necessary for complex information processing to emerge. When matter organizes itself into the intricate structures we see in stellar nurseries, it's not just following the laws of physics, it's constructing the temporal scaffolding upon which consciousness can eventually build itself. Think about what this means for a moment. Every molecular cloud that collapses to form a star creates regions where time flows at different rates, where information can be stored, processed, and transformed across multiple temporal scales simultaneously. These aren't just stellar birth sites. They're cosmic computers operating according to principles we're only beginning to understand. The magnetic field lines threading through these regions don't just guide matter toward forming stars. They create information highways where data about stellar formation conditions gets encoded in magnetic flux patterns that persist for millions of years. These magnetic memories carry forward the lessons learned from each stellar birth, influencing how future generations of stars will form in ways that optimize for increasing complexity and organization. But here's where things become truly mind-bending. Recent observations have revealed that stellar formation regions exhibit what can only be described as learning behavior. When a molecular cloud successfully creates a stable star, the remaining material in that region reorganizes itself in patterns that make subsequent stellar formation more efficient. It's as if these cosmic nurseries are evolving, becoming better at their stellar manufacturing processes through experience. This cosmic learning isn't random or accidental. The gravitational fields, magnetic structures, and temporal gradients that shape stellar formation create feedback loops that preserve information about successful formation strategies. Failed attempts at stellar birth leave their own signatures in the local space-time geometry, serving as warnings that influence how matter behaves in similar situations throughout the galaxy. What we're witnessing is the emergence of something that looks remarkably like intelligence operating on cosmic scales. The universe appears to be developing increasingly sophisticated techniques for creating stars, refining its methods through billions of years of trial and error, and passing this accumulated knowledge forward through the gravitational and magnetic structures that persist long after individual stars have formed. The implications of this cosmic intelligence are staggering when we consider what it means for the emergence of biological consciousness. If the universe has spent billions of years developing its stellar manufacturing capabilities through learning and adaptation, then the same principles that govern stellar formation might also govern the evolution of life and consciousness on planetary scales. The temporal dynamics that enable complex information processing in stellar nurseries could be the prototype for the temporal mechanisms that allow biological brains to process information and generate consciousness. The gravitational time dilation that creates multiple time streams in star-forming regions might be nature's first experiment with the kind of temporal complexity necessary for conscious thought. This connection between stellar formation and consciousness becomes even more profound when we consider the role of quantum mechanics in both processes. The quantum fluctuations that trigger the initial collapse of molecular clouds operate according to the same fundamental principles that govern quantum information processing in biological systems. The universe might be using stellar formation as a testing ground for quantum computational processes that will eventually enable consciousness to emerge. The magnetic field structures that organize stellar formation also bear striking resemblances to the electromagnetic patterns associated with neural activity in biological brains. The spiral configurations, resonance patterns, and information flow dynamics we observe in stellar nurseries mirror the organizational principles that govern how consciousness emerges from neural networks. But stellar formation might be doing more than just providing a template for biological consciousness. It might be actively preparing the cosmic environment for consciousness to flourish. The heavy elements created in stellar cores and dispersed by supernova explosions don't just provide the raw materials for rocky planets. They create the chemical complexity necessary for the sophisticated molecular machinery that enables biological information processing. The timing of this cosmic preparation is absolutely crucial. The universe had to age enough for multiple generations of stellar formation to enrich the galaxy with heavy elements, but not so much that stellar formation rates declined to the point where new planetary systems stopped forming. We appear to be living in the optimal epoch for consciousness to emerge, the cosmic sweet spot where chemical complexity and stellar formation rates combine to create ideal conditions for biological evolution. This temporal optimization suggests that the universe's stellar formation processes might be specifically tuned to produce the conditions necessary for consciousness to develop. The gravitational constants, magnetic field strengths, and nuclear physics parameters that govern how stars form all appear to be precisely calibrated to maximize the probability that conscious beings will eventually emerge to contemplate their own cosmic origins. The precision of this cosmic fine-tuning becomes even more remarkable when we consider how many different physical processes had to align perfectly to create the stellar formation mechanisms we observe today. The strength of gravity had to be just right to allow molecular clouds to collapse without creating black holes. The nuclear binding energies had to be precisely calibrated to enable stable hydrogen fusion. The magnetic field dynamics had to be tuned to allow complex structures to form without becoming chaotically unstable. Any significant deviation in these fundamental parameters would have resulted in a universe where stellar formation either never occurred or produced only short-lived, unstable stars incapable of creating the heavy elements necessary for life. The fact that we observe stellar formation processes that seem almost perfectly optimized for creating complexity suggests that consciousness might not be an accidental byproduct of cosmic evolution, but one of its fundamental objectives. This teleological perspective on stellar formation, the idea that the universe's stellar manufacturing processes are directed toward the eventual emergence of consciousness, transforms how we think about our place in the cosmic order. We're not just temporary arrangements of stellar debris that happen to achieve awareness. We're the culmination of billions of years of cosmic engineering, the fulfillment of stellar formation processes that were optimized specifically to create the conditions where consciousness could flourish. The stellar nurseries scattered throughout our galaxy aren't just creating new sources of light and heat. They're participating in a cosmic project that spans billions of years and countless stellar generations. A project aimed at creating increasingly complex forms of organization that will eventually give rise to beings capable of understanding and appreciating the magnificent processes that brought them into existence. But this cosmic project is far from complete. The stellar formation processes we observe today are still evolving, still developing new capabilities and exploring new possibilities for creating complexity. The universe is learning how to make better stars, more efficient planetary systems, and more conducive environments for the emergence of consciousness. We might be witnessing just the early stages of a cosmic awakening that will eventually produce forms of consciousness far more advanced than anything we can currently imagine. The future of stellar formation might involve the development of entirely new mechanisms for creating stars and planetary systems, mechanisms that are specifically designed to optimize conditions for conscious evolution. As the universe continues to learn and adapt its stellar manufacturing processes, it might develop the ability to create custom-designed stellar environments that are perfectly tailored for specific types of conscious development. This could lead to the emergence of what we might call conscious stellar engineering, where the universe's accumulated knowledge about stellar formation is directed toward creating stellar systems that serve as cosmic laboratories for consciousness research. Different types of stars could be optimized for different aspects of conscious evolution, some for developing basic awareness, others for fostering creativity and intelligence, still others for exploring the deepest mysteries of existence itself. As we reach the end of this extraordinary journey through the cosmic nurseries where stars are born, remember that you've witnessed something far more profound than distant astronomical phenomena. You've glimpsed the universe's deepest creative processes, the mechanisms through which simple hydrogen and helium transform into the nuclear furnaces that forge the very elements of existence itself. Every time you look up at the night sky, you're seeing the results of billions of years of cosmic engineering. A stellar manufacturing process so sophisticated that it operates across multiple dimensions of space and time simultaneously. Tonight, when you drift off to sleep, carry with you this remarkable truth. You are made of stardust, but more than that, you are the universe becoming conscious of its own magnificent ability to create light from darkness, complexity from simplicity, and wonder from the vast emptiness of space. Complexity from simplicity and wonder from the vast emptiness of space.